Hello. As we have already talked about the crystal system, possible variations, axial distance of edge lengths, axial angles, and their examples, and also about these unit cells, 14 types of Brevis lattice. Now moving on to primitive cubic unit cell. So if you have one atom, then if you put the sphere, you assume it like a sphere, and you put the atom at the center of a cube, assuming at the center of the cube, and then you proceed to find the structure of the solid or the unit cell of the solid. That is called the primitive cubic unit cell. Okay, and here are some examples how it looks. Body centered cubic unit cell, you have one body centered, you have one atom at the body center of the cube and 8 on the edges. And if you want to find out total number of atoms present on the primitive cubic unit cell, then you might like to assume the primitive unit cell to be like this, where there is one atom at the body center of the cube and 8 pieces of the sphere on the edges, so that you can find out how much part of the sphere is actually inside the primitive cell that is under consideration. Face centered, especially now face centered is like this, where the atom is shared between two cubes. So half is counted on the left one, half is counted for the right one. Closed packed structures. Closed packing in one direction. Closed packed structures. In solid, the constituent particles are closed packed. That's why they are solid. There is not enough movement between the atoms. That's why they are solid, and minimum vacant space between the atoms. Let us consider the constituent particles as identical Hart pairs and build up the three-dimensional structure in 3 steps. A closed packed in one dimension, so you just keep on putting the identical pairs or the atoms in one direction, or just one after another. That's how you get the closed packing in one dimension. And similarly, you can imagine it how it would be in the second or two directions, sorry, in 2D. But a little difference, like generally we assume this one, like when we said the close packing of the 1D is a single line, or the structure like A, where you just keep on putting atoms one after another. Then what thought comes in our mind for the 2D is the A1, and we might forget this part where you can also put the atoms in the dome shaped area, or the void region between the two. You don't have to touch the space directly, space to you don't have to make this sphere line as well in 1D closed pack. There are two types of structures in in 2D. That's the main point. Third one, closed pack in 3D. 3D, it might have so many different cases. As we go from 1D to 2D and 2D to 3D, the cases will just going to increase because you have different options of arranging those pairs in different space, and in more space you can arrange them in different styles, so that you will have different type of structures. So first of all, it is like the AAA arrangement, where you just keep on putting the 2D A, that is 2D, the structure we studied, the first 2D structure that we studied, you just keep on repeating those structures one after another, layer by layer, so you'll get the first three-dimensional closed pack structure. Second, three-dimensional closed packing from two-dimensional hexagonal closed packing layers. So as we already did from the two-dimensional A part, then we have to do it from the hexagonal 2D arrangement also. Then you also keep on, but in this case, you might put the spares exactly on top of the another spare, or you might put the another spare in the void between these three spares of the first layer, so you will get different structures in the second part. A, placing layers over the first layer, you just keep layer by layer, so just keep the layer symmetrical. You put the spare exactly to the same position as it was in the first layer. And the B part, I'm sorry, it has some interesting point as well. You can name those voids differently. Okay, these voids are called tetrahedral because a tetrahedron is formed when the centers of these four spheres are joined. They have been marked as T in the figure 1.16. One such void has been separated separately in 1.17. And then you put the another layer. This is only we are talking about the second layer, that is we are putting on the first layer to get a three-dimensional structure. Now you put the third one, you will get a tetrahedral hole or tetrahedral void, anything, where usually the cation ion comes, and the structure we usually talk about are generally made by anions. So these void are important because these are the location of the cations of the compound. 8 other places, the triangular void in the second layer are above the triangular voids in the first layer, and the triangular shape of these do not overlap. One of them has the apex of the triangle pointing upward and the other downwards. These voids have been marked as O in figure 1.16. Such voids are surrounded by 6 pairs and are called octahedral void. One such void has been shown separately in figure 1.17. The structure of these two types of void depend upon the number of closed packed pairs. Let the number of closed packed pairs be n. Then the number of octahedral voids generated is equals to n, and the number of tetrahedral voids generated is equals to 2n. Now you might understand the logic, and I will tell you the logic, but it is very important, so that very important to remember these formulas. The number of octahedral voids generated is n. And what is n? N is the total number of voids. No, sorry, I just messed up. And we are considering the octahedral voids generated is equals to n, and the tetrahedral voids will be twice the number of octahedral voids generated. Now logic. As we are putting on the second layer, this void is already there. Okay, this void is already there when we are going to put the third layer over the second one. So when you already got tetrahedral void or hole, and when you're putting the second third layer actually, then you get a uh, octahedral void. So just by common sense, I guess you can simply say that after a third layer we get a octahedral void, and the tetrahedral void is just repeating continuously after one layer to the another, whereas the octahedral void comes once in three layers. So twice the number of octahedral holes. You can simply find this out by common sense. Placing third layer over the second layer. First, covering tetrahedral voids. Tetrahedral voids of the second layer may be covered by spares of the third layer. In this case, the spares of the third layer are exactly aligned with those of the first layer. Thus, the pattern of spares is repeated in alternate layers. This pattern is often written as AB pattern. This structure is called hexagonal closed packed structure (SCP). This sort of arrangement of atoms is found in many metals like magnesium and zinc. So covering tetrahedral voids, you place the third layer of hexagonal type, the second hexagonal layer. Do keep that thing in mind that we are making these with the help of 2D hexagonal layers. Okay, these 3D structures are made from 2D layers, and these 2D, especially these 2D that we are now studying, are made from hexagonal 2D structures. Hexagonal and cubic. Second, covering octahedral void, the third layer may be placed above the second layer in a manner so that its spares covers the octahedral void. When placed in this manner, the spares of the third layer are not aligned with those of either the first or the second layer. This arrangement is called C-type. Only when fourth layer is placed, its spares are aligned with those of the first layer as shown in figure 1.18 and 1.19. This pattern of layer is often written as ABC. This is called cubic closed packed CCP or face centered cubic FCC structure. Metals such as copper and silver crystallize in this structure. Both these types of closed packed are highly efficient, and 74% space in the crystal is filled. In either of them, each pair is in contact with 12 pairs. Thus, the coordination number is in either of these two structures. Earlier in this section, we have learned that when particles are close packed, resulting in the either HCP or CCP structures, two types of voids are generated, while the number of octahedral voids present in a lattice is equal to the number of close packed particles. Closed packed particles. Particles are closely packed in solids, so the number of closed packed particles in the primitive cell, that we are talking about primitive cell for like the entire chapter, no? That's the way to study solids. You can study solid without primitive cell, especially now. You might find some other method in college or somewhere, or for your level you have to understand now only this method. The number of tetrahedral voids generated is twice this number. In ionic solids, the bigger ion, usually anion, from the closed packed structure, and the smaller ion, usually cation, occupy the void. Because cations are small in size, so they can fit in between the anions, in between the voids that are formed by the anions. If the lattice sign is small enough, then tetrahedral words are occupied if bigger than octahedral words. Not all octahedral or tetrahedral words are occupied. In a given compound, the fraction of octahedral or tetrahedral words that are occupied depend upon the chemical formula of the compound, as can be seen from the following examples. Yeah, the CCP, oh sorry, a compound is formed by the two elements. Atom of the element Y makes CCP and those of element X as cations occupy all the octahedral words. What is the formula of the compound? So the total number of Y, or the closely packed particles, as we like to call, and so the number of Y is equals to the total number of octahedral words. So the ratio of those elements will be 1:1, and the compound formula will be xy. And if the the cation occupied would have occupied the tetrahedral words, then it would be x to y. You know why? Because the number of close packed particles, the number of tetrahedral words is twice the number of the closely packed particles, that is y. So x would have been 2 times of y, so x to y would have been the structure. Now similar example you might do by yourself. Locating tetrahedral and octahedral words. We know that the close packed structures have both tetrahedral and octahedral word. Let us take CCP or FCC structure and locate these words in it. Locate tetrahedral words. Let us consider a unit cell of CCP or FCC lattice. The unit cell is divided into 8 small cubes. Each small cube has 8 alternate corners. In all such, each small cube has 4 atoms. When joined to each other, they make a regular tetrahedron. Thus, there is one tetrahedral word in each small cube and 8 tetrahedral words in total. Each of 8 small cubes have one word in one unit cell of CCP structure. We know that CCP structure has 4 atoms per unit cell. Thus, the number of tetrahedral words is twice the number of atoms. You might have get it because this is really easy. If you imagine, and we have already discussed that you imagine yourself the primitive unit cell is cubic, and if you imagine anions to be placed like face centered, then you get the structure that is given here. And now you divide that cube into 8 different cubes, equal size cube, and in the given format. So if you take one of those 8 cubes and join those anions or the particles, then you will get the tetrahedral structure, and the void that is present between them is the tetrahedral void. That is so simple, I guess. And locating octahedral words, this is little different, but you might understand. Let us again consider a unit cell of CCP or FCC lattice. The body center of the cube C is not occupied, but it is surrounded by 6 atoms on face centers. If these face centers are joined, an octahedral is generated. Thus, this unit cell has one octahedral void at the body center of the cube. Beside the body center, there is one octahedral void at the center of each of the 12 edges. It is surrounded by 6 atoms, 3 belonging to the small unit cell, 2 on the corners and 1 on the face center, and 3 belonging to the adjacent unit cells. Since each edge of the cube is set between 4 adjacent unit cells, So is the octahedral void located on it. Only one fourth of each void belong to a particular unit cell. Now listen this carefully, okay? We are taking a face-centered primitive unit cell. The unit cell where you get one atom at the face, at the center of the face, each face of the cube. And now, if you join centers of those anions or particles, those are placed on the face, all the faces of the cube, then you will get an octahedral, and the void will be octahedral void. So will be at the center of the cube where you get the octahedral void. And similarly, you don't stop there. If you imagine yourself drawing those uh, same structure above, behind, left, right, everywhere around on the 8 faces, you will get 8 more, but a small part of, like in the B, as you see, for the another primitive unit cell, this is the central octahedral void. Sorry, it's not I'm sorry, it's not. But if you imagine yourself drawing this, then you find one octahedral void at each of the edges. So you get 8 more octahedral voids, but only 1/4 of each void belong to a particular unit cell. So how many octahedral voids you get? One at the center, 1/4 at how many edges? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 into 1/4 is 3, and 1 at the center is 4. You get 4 octahedral voids, and simply doubling the number you get the tetrahedral voids. Or it's easy to find tetrahedral voids than just half the number. Okay, so moving on, in whatever way the constituent particles, atoms, molecules, or ions are packed, there is always some free space in the form of voids. Packing efficiency is the percentage of total space filled by the particles. Let us calculate the packing efficiency in the different parts of structures. Both types of closed packing, HCP and CCP, are equally efficient. Let us calculate the efficiency of packing in CCP structure. In figure 1.20, let the unit cell A's length be A and the phase diagonal AC equals to B. Okay, in triangle ABC, AC square is equals to B square, that is equals to BC square plus AB square, simply by Pythagoras theorem, and B is equals to root 2A. So simple. If R is the radius of the sphere, we find B is equals to 4R is equals to root 2A. A is equals to 4 up or upon root 2, that is equals to 2 root 2R. We can also write R is equals to A upon 2 root 2. We know that each unit cell in the CCP has effectively 4 spheres. Total volume of 4 spheres is equals to 4 into 4 by 3 pi r cube, and the volume of the cube is a cube, or 2 root 2 r whole cube. Packing efficiency is defined as volume occupied by 4 spheres in the unit cell into 100 upon total volume of the unit cell. Now 4 is a random number. You might imagine how you can just take 4 spheres volume. Okay, volume occupied by 4 spheres in the unit cell into 100 upon total volume of the unit cell. So the packing efficiency physically understanding what is the packing efficiency is how tight the structure is, how tightly packed the structure of the solid is. How will you find that? You select the primitive unit cell and you take this one portion of this primitive unit cell and you find the volume that is occupied in a given volume, in a given well defined repetitive volume throughout the solid. So by doing that, you can simply say the volume occupied by four spheres. Where these four spheres come from? There are four atoms inside this cubic unit cell. So four, you need to find out the volume of four spheres and divide it by the total volume of the unit cell, and you will get the packing efficiency. Packing efficiency in this case is calculated for this given CCP structure. It will vary on different. It will vary based on the different structures. Obviously, that's why we need to find out which is more packed and which is not, or which packing efficiency is more good, and all that stuff. You might also would like to go through this calculation, or maybe not, but you have to remember some of the things. Like, this is generally asked question that you might remember, like this is almost 74%. You don't have to, but you can just calculate it. But they may directly ask this question, and other students might remember this, and they just, for them it is just 1 second question. They just see and they just click and they move on, and you might just sitting there for 2-3 minutes and wasting your time. 74% for this type, HCP and CCP are equally efficient, and the packing efficiency as calculated is 74%. It's not exact, but it's almost. Efficiency of packing in body centered cubic structures, BCC. From figure 1.21, it is clear that the atom at the center will be in touch with the other atom diagonally arranged. In triangle EFD, as you see here, EFD, you see at the bottom face, EFD. This triangle B square is equals to A square plus A square is equals to 2A square. BCC, these two sides are same, and so the diagonal is B, so B is root 2A. Now in triangle AFD, A, F and D, you see this triangle, this is root 2, this is root 2A, this is A, and we have to find AF, that is root 3A, and you will find all the dimensions basically by doing this. In this type of structure, total number of atoms is 2 and their volume is 2 into 4 by 3 pi r cube. And sorry, I should explain how you calculate the relation between space radius and the side of the primitive unit cell. The length of the body diagonal C is equals to 4r, where r is the radius of the sphere or atom. As all these three spheres along the diagonal touch each other, Therefore, root 3a is equals to 4r. Okay, is equals to c. Thus we know you find variables in different form of variable and in the same variable, sorry, and then you compare it. So you get r is equals to root 3 by 4a. In this type of structure, total number of atoms is 2 and their volume is 2 into 4 by 3 pi r cube. Volume of the cube a cube will be equal to 4 by root 3 r whole cube, or a cube is equals to 4 by 3 root 3 r is equals to whole cube. Sorry, therefore packing efficiency, volume occupied by two spheres in the unit cell into 100, total number of unit cells, total volume of unit cells, sorry, 2 into 4 by 3 pi r cube into 100 upon 4 by root 3 r whole cube, 8 by 3 pi r cube into 100 upon 64 3 root 3 r cube is equal to 58%. So for BCC, the packing efficiency is 68%. Remember that one as well. In a simple cubic lattice, the atoms are located only on the corners of the cube. The particles touch each other along the edge. Thus, the edge length or side of the cube A and the radius of the each particle are related as A is equals to R. The volume of the cubic unit cell a cube is equals to 2r whole cube is equals to 8r cube. Since a simple cubic unit cell contains only one atom. What? Since a simple cubic unit cell, you remember the first thing that we learned is simple cubic unit cell contains only one atom. The volume occupied of the space is equals to 4 by 3 pi r cube. Packing efficiency is equals to volume of one atom upon volume of the cubic unit cell is into 100, and you will get approx 52.4%. Thus we may conclude that CCP and HCP structure have maximum packing efficiency. And then you have BCC with 68%, and then you have packing efficiency in simple cubic lattice, and that comes around like 52%, 52.4%. And the point, the simple cubic unit cell, the spheres are in contact with each other along the edge of the cube. In some cases it might not be. Okay, calculations involving unit cell dimensions. From the unit cell dimension, it is possible to calculate the volume of the unit cell. Knowing the density of the metal, we can calculate the mass of the atom in the unit cell. The determination of the mass of a single atom gives an accurate method of determination of Avogadro constant. Suppose edge length of a unit cell of a cubic crystal determined by X-ray diffraction is A, D, the density of the solid substance, and M, the molar mass. In the case of cubic crystal, volume of a unit cell is equals to A cube. Mass of the unit cell is equals to number of atoms in the unit cell. Mass of each atom is equals to Z into M. Here Z is the number of atoms present in one unit cell and M is the mass of a single atom. Mass of an atom present in the unit cell, that's simply small m is equals to capital M upon Na. You already read this in 11th class, first chapter, I guess. Therefore, the density of the unit cell is equals to mass of unit cell upon volume of the unit cell. Density is mass upon volume, yeah, of course. Z m upon a cube. Z capital M upon a cube and a, or D is equals to Z capital M upon a cube and a. Remember, the density of the unit cell is the same as the density of the substance. What? The density of the unit cell is the same as the density of the substance. Just because the symmetry, that's why we are studying about the primitive unit cell for this long, or will be continue reading, because this defines the property of the whole solid. So density of the solid can also be determined by other methods. Out of five parameters Z, D, M, capital M, A, and Na, if any four are known, we can determine the fifth. And then you have some questions. An element has a body-centered cubic structure with a shell edge of 288 picometers. The density of the element is 7.2 gram per centimeter cube. How many atoms are present in 208 gram of element? Hmm. So volume of the unit cell is 288 picometers whole cube. Then you calculate it comes out to be 2.39 10 to the power minus 23 centimeter cube. Volume of 208 gram of the element is equals to mass upon density, that is 28.88 centimeter cube. Number of unit cell in this volume is equals to 28.88 centimeter cube upon 2.39 into 10 to the power minus 23 centimeter cube per unit cell. That comes out to be 12.08 into 10 to the power 23 unit cells. Since each BCC cubic unit cell contains 2 atoms, therefore the total number of atoms in 208 gram, that is equals to 2 times atoms per unit cell into 12.08 into 10 to the power 23 unit cells. That comes out to be 24.16 into 10 to the power 23 atoms. X-ray diffraction studies. We have already done that one. The example is done. Okay. X-ray diffraction study shows that the copper crystallizes in an FCC unit cell with the cell age of 3.608 in 10 to the power minus 8 centimeter. In a separate experiment, copper is determined to have a density of 8.92 gram per centimeter cube. Calculate the atomic mass of copper. In case of FCC lattice, number of atoms per unit cell Z equals to 4 atoms. Therefore, M is equals to D and AQ upon Z. 8.92 gram centimeter cube into 6.022 into 10 to the power 23 atoms per mole into 3.608 into 10 to the power minus 8 centimeter whole cube upon 4 atoms. That comes out to be 63.1 gram per mole. Atomic mass of copper is 63.1 AMU, atomic mass units, or mu. Similar examples, you can solve them. And I guess this should be it for now. Imperfections in solid, we will continue on in third lecture, I guess.